to all of you. I hope I'm audible and visible to everyone. Yes, a very good morning to everybody. Okay, so I hope all of you are doing well. Yes, once again, a very good morning to whoever is in this session. And I hope all of you have like a better gain from this session. And today we are going to start off with the new chapter, which is basically periodic classification of the elements. Periodic classification of the elements. And this chapter is very, very important because the thing is, as far as your block chemistry is concerned, right? So basically you should have a kind of a better understanding or else a better grip on this particular periodic classification as well as chemical bonding chapter. And that way only you will be able to, sail very smoothly through this chapter. Now, in today's session, we are basically going to learn about very basic fundamentals. Okay. In fact, many of the things you might be knowing because we are being studying it from basically 9th standard, right? So it's basically, you might have guessed what is the topic for today. Basically, it is the development of the modern periodic table, right? So starting from who gave it and all those stuff, we are going to cover in today's class. Okay. Now, so let us put the heading as development of modern periodic table. Now, in that first one is Dauberniers triad. Right? As such, there was like Lavoisier who basically differentiated the elements classified broadly, right? But the thing is, we are going into all those kind of, contribution from the scientists, which were like slightly meaningful and which is there in your syllabus. Okay. Now, when it comes to Daubernier triad, as the name suggests, who was the scientist behind this? He was Daubernier, right? And when it comes to triad, triad means, as the name suggests, group of three. That is triad. Okay. So what he did, basically, he took certain elements which showed certain similarity in their properties, and he grouped them into a group of three, and that group of three was known as triad. Okay, and what was the speciality about this triad? That basically the atomic mass of the middle element was the average of the atomic mass of other two elements. That's how he made the triad. Okay, so let us write this down. So he arranged the elements. He arranged the elements in the group of three, in a group of three, which is known as triad. And in fact, it will be better to write down, he arranged the similar elements. Similar elements means the elements having the similar properties, okay? So, which is known as triad, okay? The atomic mass of, and we can write like this, in these triads, the atomic mass of the central element, the atomic mass of the central element is average of the other two elements. Average of the atomic masses of other two elements. Atomic masses of other two elements. Right? So for example, let us say one example I am giving you. First triad, in fact, lithium, sodium, potassium, right? Now this is the middle element over here, right? Now the thing is lithium, if at all I consider the atomic mass of it, it is 7, this is 39. So if at all you want to find out the atomic mass of sodium, so according to Dauvergne, what he said, that the central element, its atomic mass is average of these two. That means 7 plus 39 upon 2, that is 46 upon 2, which is 23. And that's how you know that the atomic mass of sodium is 23 AMU, right? Now, basically, when he clubbed them together, they showed similar properties, right? They have same number of valence shell. They were very reactive, right? And they all were metals. So like that, he has grouped the elements in the basically triad form. Now the other triad forms, I'm just writing the name of them, right? And the similar concept is there: calcium, strontium, and barium. Then the another triad which he made was chlorine, bromine, and iodine. Here it is 127, 35.5. You would have got 80 here, right? Here it is 40, then 137, and then you are having here 88. Right, I'm directly writing these are the few triads which are mentioned in your NCRT, and you must, kind of pay attention to that. You must remember also. Okay, now the thing is, what were the demerits? Merit is okay, fine. Merit is at least somebody tried to classify certain elements together. Right. Now the thing is, what was the demerit? First of all, it couldn't be applied to all the elements which were there. Right. So it was only limited to certain number of them. Okay. So we can write down not valid for all the elements. And the second one was certain wrong triads were also made. Certain wrong triads were also made. Right? For example, suppose if at all I am saying carbon, nitrogen and oxygen, right? Atomic mass, if you see, it is 12, it is 16, and when you take the average, it is 14. So according to that atomic mass rule, it is satisfying that the atomic mass of the central element is average of the other two. It is satisfying that. But the thing is, altogether, these three elements, they are not showing any similarity in their properties, which you already know. In group 14, it will be, in group 15, it is, at group 16, there is lots of dissimilarity in their properties. Getting it? So valence shell electrons 4, here it is 5, here it is 6. So the property wise also they are different. Whereas the earlier triads which he has made and declared his law, they were showing certain properties, similarity in the properties. Like them, they are all non-metals, right? And the thing is, they are having like 7 valence electrons. Here, they are all metals. They all form +2, like ions in the +2 state, right? So there was similarities, but here this was a wrong triad. Getting it? So this is the demerit, and I hope this Dauvergne triad is clear to you. Okay. Now let us move on to the next one, which is Newland's law of octaves. Right. So basically, Newland's law of octaves, from where this has been taken care of, basically we have musical octaves, right? Those of you who are, kind of having certain inclination towards music, learning music, so you must be knowing that sa re ga ma pa dha ni sa, right? So there are like 8 notes, right? So the 8th note is similar to the first one. So that's what he said, that if at all the elements are arranged according to the increasing atomic masses, then the every 8th element property will be similar to the every first one, the way every 8th note in a musical octave is same as the first one. That's what was the concept given by Newland's law, right? So we'll write down that. So we'll write down, if the elements are arranged in the increasing order of their atomic masses, then the property of every eighth element is similar to that of the first element, right? So basically, if we want to see here, it was lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, right? Now the thing is, here if I talk about this element, sodium, right? So its property, it is the eighth element. If you see 1, 2, 3, 4, 5, 6, 7, 8, right? So the property of this eighth element is same as that of the first element, which is basically lithium. You can count from anywhere. If at all you take magnesium, 1, 2, 3, 4, 5, 6, 7, 8, you land up with the magnesium, beryllium. So basically the property of magnesium is similar to that of beryllium, and even we know that, okay, because we know about modern periodic table slightly, right? So in the groups, basically we keep only those elements which show similarity in their property. Getting this clear? Now the thing is, you might be wondering why I have written up to this only, up to calcium. Because the thing is, there is a limitation for new land. It is not again applicable for heavier elements. It is only applicable up to like lighter elements and up to calcium only. Getting it? So we'll write down that. What are the demerits here? Demerits, first one, not applicable for heavier elements. Valid only for lighter elements. Second one, valid up to only calcium. Valid up to only calcium, right? So these are the few demerits of your Newland's law of octaves. Now next contribution comes from Lothar-Meyer's classification . So basically, Mendeleev and Lothar-Meyer, they were actually working on the same thing, but they were kind of, in different parts of the world. So earlier days, it never used to be like Instagram, Facebook, or else, kind of Snapchat, all those things. So people never used to, they were not able to kind of communicate what they are researching on, unless and until there used to be some kind of convention where they scientific convention where so many scientists will come and they'll kind of discuss the works which they have done, right? So that was the reason Lothar-Meyer is not given that much of the importance, as far as like everybody knows about Mendeleev, but not many people know about Lothar-Meyer contribution. But definitely his contribution cannot be cannot be ignored. Now, when it comes to Lothar-Meyer classification, what he did, basically, he tried to plot. He was like, his classification was based on, kind of the, how the physical properties, they were varying with the atomic masses, right? Initial, whatever classification was given, it was mainly based upon the atomic mass. Okay. So what he did, he plotted the curve of physical properties like atomic volume or melting point or else boiling point versus the atomic mass, right? And then he tried to conclude certain things, and basically whatever is the conclusion he has given it in the form of a curve, right? That means the elements which are showing similar properties, they are occupying the similar positions on the curve. So that's how he could conclude, okay, they are having certain similarity in their properties. Okay, now when I talk about density is mass upon volume, right? When I talk about atomic volume, so what I can say here, it is mass upon density. Can I write that? So solid state density will be there, or else the density of the element can be easily identified. Their mass we already know. So that's how he got to know about the atomic volume. Okay, and then when he plotted the graph for atomic volume versus the atomic mass, right? So he could get something like this, right? So it is like the peaks of these curves, lithium, sodium, potassium, rubidium, cesium, right? The peaks of this curve was occupied by alkali metals, and the troughs or the base, they were occupied by transition elements, right? And then the thing is fluorine, chlorine, bromine, you are having iodine, right? So ascending position, that was occupied by halogens. You are having descending position, beryllium, magnesium, calcium, strontium, and barium, like that, right? So basically what you are able to see, now you are able to relate, because the thing is you are having your modern periodic table concept where you already see lithium, sodium, potassium, rubidium, cesium in the same particular group, so now you should be able to relate that with the limited resources he could basically get to this conclusion that the elements which showed similar properties, they occupied the similar position on the curve. You're able to see alkali metals on the peak, transition elements on the bottom of this, or else the trough we say for a wave, right? And fluorine, chlorine, bromine, iodine, they are on the ascending portion of the curve. Beryllium, magnesium, calcium, strontium, you know that they belong to group 2, and they are on the midpoint of the descending curve, right? So I'll just write down here that elements having similar properties, occupied similar position on the curve, right? So basically, if at all I talk about alkali metals, which is like group 1 metals, alkali metals, peak of the curve. This is only for extra knowledge, nothing else, right? Then alkaline earth metals, basically they occupied the midpoint of the descending curve. And when it comes to basically halogens, they occupied the ascending curve, midpoint of that, and transition elements, they occupied the bottom of the curve, right? So basically from their relative position, people got to know, okay, if they are showing similar property, they should be on the similar location. Okay, now the thing is, Lothar-Meyer definitely tried to give the conclusion, but it wasn't of that much importance. Only thing is people could relate, okay, there is some kind of similarity in their physical properties, like the elements, they are having similarity in their physical properties. That's why they are occupying the similar position on the curve. That was the one good thing which Lothar-Meyer gave. Okay. So after that, the important one which is coming up is Mendeleev periodic table. And it is important. Okay. Now definitely, who has given it? Definitely, as the name suggests, it is Mendeleev, right? And there is one important law here, Mendeleev periodic law, right? What this law states, basically, the chemical and physical properties of the elements are periodic function of their atomic masses. What does this statement means? When the elements are arranged in the increasing order of their atomic masses, then there is a kind of similarity in the properties which gets repeated, similarity in the physical and chemical properties which gets repeated after a certain regular period of time. That's what is basically Mendeleev periodic law. Okay, so we are going to write down that the chemical and physical properties of the elements is periodic function of their atomic masses, right? Their atomic masses. So definitely you are able to see that this is going to be based on atomic mass. Okay. Now let us see. And basically, Mendeleev is given a little bit more importance because whatever kind of table he suggested, first of all, major difference you can think of, Lothar-Meyer, he has just given a curve, right? And which is not of that much of practical use. But when it comes to Mendeleev, he has given a table that is of much more utility. People think that, okay, it is much more organized. They were able to relate the things there, right? And moreover, Mendeleev, he focused on the similarity in the chemical properties. That means if certain elements, if the formula of their oxide were same, they were kind of kept in one group. If the chloride's formula was same, they were kept in the same group. So it was kind of, digestible for many people. Okay. So what we are going to do here is, basically we are going to write down the characteristics of Mendeleev periodic table, PTS periodic table. First one, when he gave this table, there were only 63 elements known. Till now, how many elements are known? Till now, there are 118 elements which are known. So imagine the kind of struggle which the scientists will have to do, or else we have to do, if at all each and every element we need to, kind of read separately their like their physical properties, their atomic properties, their chemical properties. So we must be very grateful to those scientists that they have spent their entire life kind of, just discovering about the things and kind of finding the some kind of uniformity or similarity which exists, and it has taken so much of pain to give you finally the long form of the periodic table. Okay, now characteristic of Mendeleev 1, only 63 elements were present at that time. Okay, now next one, horizontal rows. There were 12 horizontal rows. Okay, 12 horizontal rows, and you can already see in your kind of NCRT there's a Mendeleev periodic table which is given to you. You don't have to remember each and everything there. Whatever are the important points, I'm telling you. Okay, so 12 horizontal rows, they were called as series, and later on these were only kind of converted into, or else called as periods, right? Later on termed as period. Okay, then there were 9 vertical columns, 9 vertical columns, right? And they were called as groups, right? Now when I talk about 9 vertical columns, it is 0 group and 1 to 8, right? And this 0 group is for inert gases. Mendeleev, he didn't include this when he was making the table, but his table was so intelligently framed that when these inert gases, they were discovered by the scientist Ramsay, it could be easily accommodated in his table, right? That's why you are able to see 0, then 1 to 8. Getting it? So inert gases, I'm writing this, later on discovered by Ramsay. He was a scientist. Okay. Now the thing is, you are having 1 to 7. 1 to 7 groups were divided into 2 subgroups. Okay. That means if at all I take 1, it was 1A and 1B, where A subgroup, that was for normal elements, and B subgroup, it was for transition elements. Okay, and the 8th group basically 8th group which was there, 8th group, it contained basically 9 elements and 3 elements in a group, actually in a row, right? It consisted of 9 elements, that is 3 elements in a row, right? So what are those? Basically you are having iron, cobalt, nickel, ruthenium, rhenium, and then you are having basically osmium, iridium, platinum. So you are having these 9 elements in this particular 8 group. So these are the basically characteristic of your Mendeleev periodic table, right? I hope you are clear about it. Now let us see what are the merits of this Mendeleev periodic table. Okay, so I'm going to write this as merits of Mendeleev periodic table. Now when it comes to merits, okay, so basically if at all you see your NCRT, in your NCRT actually they have given you kind of all those things which will be mentioned about the scientist in a boxes and colorful boxes. You must read about them, and kind of Mendeleev was regarded as a chemistry genius there, because he at that time he was able to predict certain things. He corrected some atomic masses, and he also left certain spaces in his periodic table, and which proved kind of fruitful for accommodating certain elements later on, okay, when they were discovered. So first one, he left certain blank spaces for the elements to be discovered later on, right? So basically you have to remember all those elements here, right? So you are having Ica aluminium, then Ica silicon, then you are having Ica manganese, and then you are having Ica boron, right? Now the word Ica is basically derived from Sanskrit, so basically it means first. Ica means first. So first aluminium and after that the element, so basically it is gallium. You will see that like aluminium, below that it is gallium. Silicon next to aluminium, you are having basically this as germanium. So below silicon you are having germanium. So first silicon, then germanium. Ica manganese is technetium. Then you are having Ica boron, which is scandium, right? So these 4 are important, and they could be asked to you in the examination from Mendeleev periodic table, right? They can ask you simply Ica silicon is, and they can give you 3 to 4 options. So you must know it is the case, and the thing is you must know that for them these 3 it is very easy to remember. You are having aluminium group 13, then silicon, and then in the D block you are having this manganese, right? So there just below aluminium what comes, that is basically Ica aluminium, right? Ica silicon below that which comes, that is basically Ica silicon. Only somewhat out and out is Ica boron, which is scandium. Getting it? Okay. Now next thing is, we can also say that it is a kind of better classification than previous ones. Definitely much more kind of meaningful classification. Then atomic weights of certain elements were corrected. Atomic weights of certain elements were corrected, right? Now for example, earlier, see the thing is for beryllium, equivalent weight is basically 4.5, so earlier it was considered valency of beryllium to be 3, and now that is the present one, which is the correct one, right? This is the correct one actually. Now, do we know one thing, that equivalent weight is equal to atomic weight upon the valency. You will be writing n factor, right? That's what we are writing. Now, if at all I keep here 4.5, valency of, earlier it was like, kind of assumed or seen somewhere that or else they assumed it, that this valency of beryllium is 3. So accordingly, the atomic weight of beryllium was 13.5, which was wrong actually, right? Now here, valency of element or else valency of beryllium was taken as 2, and that's how the atomic weight of beryllium, it came out to be 2 into 4.5, which is 9, and that was the correct one, right? Basically, he has arranged the elements according to the atomic masses, no? So in that case, basically he was able to see that there is some discrepancy, and that's how he changed it, okay? And it got correct, okay? So I'm just writing down corrections for atomic weight in following elements, right? These are the elements here. So basically we can remember like this, some people, they are very materialistic, they're always running behind gold, platinum, and purchasing the very, very costly things. So you are kind of, sarcastically telling those people, you be always behind gold and platinum. So that's what, you be in gold and platinum, right? So you be in gold and platinum. Getting it? So gold, platinum, indium, beryllium, uranium. So basically correction for these elements were done, atomic weight. And I hope this is clear to all of you. Please make sure you are writing. Okay. Now let us move on to demerits of Mendeleev's periodic table. Now, as far as demerit is concerned, first one is, we know that the hydrogen's place, it wasn't, kind of fixed. Because hydrogen shows that, you have already studied about, know little bit about hydrogen. So you already know that the hydrogen shows certain similarity in its property with group 1 as well as with group 17, right? So basically it wasn't decided, it wasn't sure that where to keep this particular hydrogen. So that was the first demerit, right? So we can say position of hydrogen was not certain. It could be placed in first A as well as 7A, right? Group we are talking about. Second one, now the thing is, Mendeleev, he has given his particular, classification based on atomic masses. So when it comes to isotope, so isotopes, they are having same atomic number but different atomic masses. So ideally, they should have been given different places, but there was no provision like this for that, for the placement of isotopes. So what we say that isotopes were not given any separate place in his periodic table. PT is periodic table, time and again I am telling you. Now, next one is, there were certain anomalous pairs which was found. What are those anomalous pair means? Anomalous means kind of which are not following the trend. Okay. So we are writing certain anomalous pairs were found. Pairs of element I am talking about. So these are the anomalous pairs actually. Why they are anomalous? Basically, you will come to know. if at all I talk about their atomic masses, right? So argon is basically 39.9, this is 39.1. This is 127, this is 127.5. This is 232, this is 231. This is 58.6 and this is 58.9. Now the thing is, this is the way you will see that they are arranged in the Mendeleev periodic table. But ideally what should have been happened, that argon should be coming after potassium, because the thing is its atomic mass is more, right? But it wasn't the case. You are able to see everywhere iodine less in atomic mass. How come it is placed after tellurium? Thorium, protactinium, right? 232 and 231. Thorium should have been placed afterwards, right? So these are the kind of anomalous pairs which were not, kind of following the trend. And in fact, you must remember them. And how to remember, I'm telling you. This is Amir Khan. Everybody knows, no? Amir Khan's tell Indians, your toothpaste, hai na? Toothpaste has is in bracket just to complete it, has cobalt and nickel in it. And I think you people will be able to relate to this, because the thing is, if you remember the TV ads, somebody is, just got up and they're trying to, kind of brush their teeth, and some anchor, they'll jump into the bathroom itself, or else, kind of from somewhere they'll appear and they'll say, does your toothpaste contain salt? Right? So the thing is, in place of salt, you remember that Amir Khan, famous actor, right? So he's telling Indians that your toothpaste is containing what? Cobalt and nickel, not the salt, right? So you'll be able to remember what are the pairs of the elements which shows or else which deviate from the trend, okay? Now, next one you are having basically like elements. That means the element which showed similar properties. I'm calling them as the like elements, okay? Like elements were placed in different groups. For example, you are having gold and platinum, है ना? So this was placed in first group and this was placed in 8th group. They both are metals, है ना? Noble metals we say, because they don't react, है ना? So we are saying noble metals actually. You might be seeing people wearing gold and it's not getting affected by corrosion or anything. It is least reactive. Platinum, like many places, even platinum, ornaments are there, and, electrodes and many things will be kind of made using this platinum, right? So they are noble metals. They are having, kind of similarity in their properties. They are not very reactive, but still they were kind of showing similarity in their properties, and they were put very, very far away from each other, right? Another one, which is unlike elements were placed in the same group. That means, suppose if I talk about first group, now you already know that the groups are subdivided into subgroups. One is 1A, another one is 1B, right? For 1A, basically you can take lithium, sodium, potassium. For 1B, in fact, in your periodic table, Mendeleev periodic table, you will see that if at all I am talking about first group, like this, it will be written A and B. 1A group elements here and 1B here, right? And here you are having copper, Ag, Au. So basically these are coinage metals. They are not reactive. Now when it comes to this, they are alkali metals. And they are highly reactive. Okay. Basically, your teachers might have told you that, okay, sodium and all those things don't directly put in the sink of like your lab, where if at all you perform the experiment, because it catches fire, it is like kind of so much reactive, right? So the thing is, they are way far apart, kind of in their behavior, in their chemical properties, but still they were clubbed together. So that was one of the demerit. So I hope demerits and merits of Mendeleev is clear to all of you. Now, next classification, which is basically modern periodic table. And in fact, we'll be writing MPT, that will be better. Modern periodic table. Now the thing is, this modern periodic table, it was proposed by Moseley. Okay, he was the scientist behind this. Okay, so this was proposed by Moseley. Okay, and what he suggested, he gave modern periodic law. The way we are having modern periodic, this Mendeleev periodic law, similarly we are having modern periodic law. Now for that modern periodic law, I'm first writing down the statement of it, and then I'm going to tell you on what basis Moseley said this is the law which is going to be there, right? Now the thing is, according to this, the if at all I write this modern periodic law, I'm going to write it. We are still here only. So modern periodic law. That means the chemical and physical properties. The chemical and physical properties of the elements are periodic function of their atomic number, right? So this is what is based on what? Atomic number. Okay, so this modern periodic table, it is based on atomic number, because this kind of question can also be asked, right? Now the thing is how Moseley came to this conclusion. Basically what he did, he has different elements. Okay, he has taken those elements, and what he did, he bombarded high speed moving electrons onto its surface, and he got X-rays from that, right? And X-rays, you know that they are electromagnetic radiations, they have frequency associated with them, right? So now the thing is, he tried to kind of plot his, plot whatever experiment he has done. So what he has done, frequency of the X-rays versus atomic number he plotted for the elements, and under root of frequency, this is basically frequency of X-ray. So different elements are he has taken, and he has started kind of bombarding them with the high speed electron, and because of that bombardment of high speed electrons, he got certain X-rays, and they were having definitely frequency associated. Now when he plotted his graph with respect to atomic number, he got this as a straight line. And what about this? He got certain kind of zigzag. It wasn't a very straight line. So he came to know that definitely atomic number has to be a more fundamental property as compared to your atomic mass. And that's how the modern periodic law is based upon this particular atomic number. That means what? If the elements, they are arranged in the increasing order of their atomic number, then the elements which show similarity in their chemical and physical properties will be repeated after regular interval of time. Okay, so that's what is the meaning of this modern periodic law. Okay, so I hope it is clear. Now the thing is, characteristic of the table we'll see. Characteristic of modern periodic table. First one, it had basically 9 vertical columns. 9 vertical columns known as groups. So basically 9 vertical columns were 0, 1 to 8. Right? And here all the groups were divided into subgroup. 1 to 7 groups divided into subgroups. But this time all the subgroups were kept separately. In Mendeleev, what is the difference? In Mendeleev, he has divided 1A and 1B, but he has overall kept them in the same group, that is first group. But here it was 1A, 2A, right? I'm writing then 3A. Suppose I'm not writing in sequence, but just like that I'm showing you, 3A, 4A, 5A, 6A, right? 7A, 8th, right? 1B, I'm just writing like that, 1B, 2B and 0. That's how it was. Getting it? So all these were separate groups. I have not written them in sequence of what you see in the periodic table. Okay? I've just told you that how it will be. And second one was, it contains 7 horizontal rows which were known as periods. Okay, so that's what is modern periodic table. Now the thing is, what you are going to study is, or else what you have to remember is long form of the periodic table, right? And there only we study that there are 7 periods and 18 groups. Okay, so let us go further. In fact, I have written, I think, 5th. So we are going to write down long form of modern periodic table. Long form of modern periodic table, and this is what you have to remember, which is the most important part here. Now, basically, when you talk about modern periodic table, it has got, contribution from Moseley, right? Unless and until he would have performed this experiment, then we would not have got this law, right? And then when this long form of the periodic table was given, so there are like 3 to 4 scientists who are given credit for that. That is Ranger Werner, right? And then you are having on which thing it is basically based upon. So it is based upon basically the Bohr-Bury electronic configuration and atomic number. Why I am saying Bohr-Bury's electronic configuration? Because you are able to see that the entire periodic table which you see, which you remember, that is long form of periodic table, you are easily able to divide the elements into S block, P block, D block and F block, and that is only possible from their electronic configuration, right? So we are going to write down, it is proposed by Rang and Werner, and it is based upon Bohr-Bury electronic configuration, and atomic number. In question, if at all there is only atomic number mentioned, then also it is my humble request, please tick mark that. Okay. Now, Anna, don't say that, ma'am, you have given this, it was not mentioned in the question. The thing is, it is mentioned in NCERT, atomic number, so you basically take that. So basically, long form of the periodic table is kind of, it was like extension of that modern periodic table which came across. So what is the characteristic of long form of modern periodic table? What are those? Basically, first one will be, there are 18 vertical columns which are groups. Okay. So first one is, there are 7 horizontal rows which were called as period. And then the second one is, there were how many columns? 18 vertical columns, known as groups. So basically there are 18 groups. Okay. Here itself I am writing a note. That means we are going to see what is the relation between 1A, 2A and 1 to 18 groups which you see. So this is the latest one, and in fact you have to remember this only. Don't be in any kind of confusing zone. I have told you each and everything, but if at all it is asked in the examination for modern periodic table, so you can easily tick mark this. So they are referring always to the long form of the modern periodic table which you know. Okay. Now the thing is, what is the note I am going to write down? The relationship between the groups of modern periodic table and long form of modern periodic table, right? So basically you are having something like, according to long form of modern periodic table, there is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So I'm a little bit shifting here. 13, 14, 15, 16, 17 and 18. Now according to modern periodic table, basically it is 1A, 2A, right? And then from here, it is basically 3A, 4A, 5A, 6A, 7A, and this was like 0 group. Okay. Now, afterwards, you start off with this. For 11th one, it was 1B, 2B. And then you are having 3B here, 4B, 5B, 6B, 7B. Now for 8, 9, 10, collectively it was 8th. There was not A and D. So I think there is some sort of mistake in your NCRT. You can think of that, right? So they have kind of, mistaken for A and B. So here, maybe because of the kind of notion which they are following, but actual correct one is this one. You are supposed to write down 1A, 2A, 3A to 7A, 18th group is 0, right? This is the one which was there for modern periodic table, and which we have to follow is this. But you should have knowledge. Getting it? And A and B, you are able to see they are P block element, S block element. So S and P block element, they are representative elements, normal elements. And here, which you are able to see, they are basically transition elements whose properties are definitely different from S and P blocks. So that's why B subgroup is there. I hope it is clear to all of you. Okay. Now let us go further. So we are going to write down the characteristic of the period, group, and all those things for modern periodic table. Long form of the periodic table itself. Period. What does it tell you? That every period, if you see, first period, you are having this hydrogen, then helium. So it is like 1s1, 1s2, n equal to 2. You are writing lithium, 1s2, 2s1. So every new period starts with the filling of a new valence shell, right? New energy level. In the first one, it was the first shell which was getting filled up. In the second period, it was the second shell, and so on, right? So basically, we are going to write that first. I hope you are able to digest this. So we can say every period begins with the filling of new energy level, right? And what does this period tell you? The period corresponds to, principal quantum number. It corresponds to principal quantum number of the valence shell, right? That means, suppose if I talk about lithium, it is 1s2, 2s1. So what is the valence shell, outermost shell? Second one. And I talk about that lithium belongs to second period, right? That's what is the meaning of it. Every period corresponds to the principal quantum number. We have 4 quantum numbers now. So one being principal quantum number. So the valence shell principal quantum number corresponds to the period. Okay. Next one is number of elements in a period is going to be equal to 2 into the number of orbitals getting filled up by electrons, right? For example, and in fact we know that there are 7 periods in total. So we are going to write down basically period, number of elements. Now if I talk about first period, so in first period basically it is only 1s which gets filled up, so the number of elements is going to be 2. So we are going to write down this as very short period, or in fact shortest period you can think of. Shortest period, because it is having only 2 of the elements there. When it comes to 2, n equal to 2, you are able to see 2s, 2p getting filled up. So in 2s, maximum 2 electrons, in 2p, maximum 6 electrons. So in total, 8 electrons. So basically it is short period because it is containing how many elements? 8. And I told you that the atomic orbitals getting filled up. So there are 4 atomic orbitals which are getting filled up. And you know that the capacity of one atomic orbital is only 2 electrons, right? So that's why you are able to see 4 atomic orbitals in total getting filled up. So that's why 8 electrons and hence 8 elements. Third period also at n equal to 3, actually 3s and 3p only gets filled up. 3D is there, but it doesn't get filled up. It gets filled up after 4S, right? So we are able to say that this is also a short period. According to above principle, we don't have to violate all those things. All those things remains intact. Now n equal to 4, you are having 18 electrons. Why 18? Because you are having 4s, 3d, 4p getting filled up. 4s, 2 electrons, 3d, 10, 4p, 6. So that's how 18, right? So in fact, this is called as long period. Similarly, you are having fifth one, there also 18. You can guess easily, you are having 5s, 4d, 5p getting filled up here, 2, 10 and 6. Similarly, sixth one, it is basically 32. Why? Because you are having 6s, you are having basically n minus 1 d. So that is 5d, 4f and 6p. ns, np, n minus 1d and n minus 2f. So it is 2, 10, this is 14 and this is 6. So when you count that, this is 20, 20 plus 10, 30, 30 plus 2. So basically it is longest period, right? Similarly, seventh one, it is also having 32, right? And here you can see 7s, 60, you are having 5f and 7p. So this is also 2, 10, 14 and 6. That's how 32. And this is also longest period. The entire periodic table is actually complete, right? So I hope you understand why we are having, 32 element, which one is longest, which one is shortest. Okay. Okay. Now let us move to the next one about groups. Right? So how many groups are there? There are basically 18 groups, right? Now, when we talk about group 1, it is known as alkali metals, right? And hopefully you people know, you must be able to remember the entire periodic table. Lithium, potassium, rubidium, cesium. So basically this is Lena knows. Rugby is the game. Rugby, chess and frisbee. And these two are also the games. So basically Lena knows about that. Group 2, they are known as alkaline earth metals, right? And basically you are having here, it is beautiful mugs, can serve badam rasmalai, right? Badam rasmalai is the name of a dish actually. Now after group 1, group 2, we are going for group 13 straight away, and that is boron family. Boron, aluminium, gallium, indium and thallium, right? So basically this is like Bal Ganesh in Thailand. I'm not purposely kind of including the newer elements here, right? As such, we don't have to focus on their chemistry, right? Group 14, carbon family. So we can think of chemistry sir gives senti problems, problems which makes you sentimental. Okay, that's what I'm trying to say. So group 14 is done. Group 15, this is nitrogen family or else nicogens or else nictogens. They are having very pungent smell with them. So basically this is Nani, everybody knows him, famous actor, Prabhas, Aishwarya. Sub means it is all. Sub is a Hindi word actually. Sub big stars. So basically two of the Tollywood actors, in fact we should say Indian actors itself, Nani, Prabhas, Aishwarya, this world there, sub big stars, all big stars. Then group 16, oxygen family, or else we call it as chalcogens. That means ore forming, and that is O Salman, है ना? Salman Khan, everybody knows, no? If you want, you can write Salman Khan. O Salman Khan selling teapots. है ना? So basically, he could be a clone of him, or else a person who has a kind of similar looks to what Salman is having, right? Then group 17, which is known as halogens. Halogens meaning salt forming. So you're having fluorine, chlorine, bromine, iodine, and AT. So this is first class biryani in Atlantic Ocean. So we love our biryani so much that even going to the remotest of the place, we want it. So Atlantic Ocean. Then group 18, noble gases or inert gases. So you are having Hina, Nina, or Karina. All are like, kind of famous TV artists or actors. Ka Xerox Rangeen. Rangeen is colorful. Okay. So you must remember all these group 18 actually. Now we'll see few more. So you are having first transition series. First transition series, which is 3D series, we say. I'm telling you this because the thing is, you must be able to, remember the entire modern periodic table. That is very, very important for predicting the properties of the element. And this exercise will be definitely helpful for you for entire chemistry actually, right? And especially for inorganic chemistry. So for 3D, you are having so this is Sachin Tendulkar. Everybody knows him. Very crazy man. Why very crazy? Because he is giving free coaching, cricket coaching, okay, to Nikki's cousin. Now the thing is, you all might be knowing that this especially cricket, so if at all somebody is really interested and want to take coaching, and if at all they are from humble backgrounds, right? So at that time it becomes very difficult. So this kind of coaching will be very, very taking these kind of coaching will be very, very typical or else very tough. So in that case, Sachin, he also belongs to a humble background, so he has seen that potential of potential in Nikki's cousin sounding like cousin, so copper and Zn sound of that is there, right? So Nikki's cousin, so that's the reason he has given he has decided that okay, he'll like try to give him free coaching for that. So that's why people are calling him crazy. Okay, now the thing is, second transition series so that is 4D series. In that, you are having so the thing is, we can write yes, zebra, can never be. I'm writing just few things to, kind of complete this statement. Can never be molded technically into rude rhino, provided given silver Cadbury. The thing is, zebra is kind of a calm animal, okay? You cannot actually technically mold any zebra into rhino, which is very rude, okay? Or else very harsh. But provided if you give that zebra kind of, silver Cadbury, then he may lose his kind of, calm, or else that focus, attention, and he may start behaving like rude rhino. Okay, so you can remember like that. And if at all you are having any of your own mnemonics, you can also have it. Now, the thing is, third transition series, which is we write 5D series. So we are writing so this is like latest half talking women researched, right? So hearing that Osama, Osama is the terrorist actually. Osama got irritated, put gold is AU in mercury, mercury is HG. Getting it? So basically, normally women basically, they are always kind of, associated with being called as chatterbox. Not everybody is like that, but I'm saying that in general, right? Now the thing is, so when Osama, he came to know that there is some kind of, half talking, very less talking women, that kind of women researched, so it kind of blew his mind. That means he got irritated. Irritated. So in that irritation, what he did, he has basically put in that irritation a very costly metal, which is gold, in mercury. Mercury is not that much costly, right? Getting it? So that's what you can remember. Now next is fourth transition series, which is 6D series. We are writing 3D, 4D, 5D series. That means the electrons are getting progressively filled up in those orbitals, and 6D 1 to 6D 10 like that. Okay, I hope that point is very clear to you. Actually, Rutherford dubbed a song behind his metro in Darmstadtium. Roger can never have. So did we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Okay. Now the thing is, this is actually RF is Rutherfordium, but we are writing Rutherford. This is dubnium, so we are writing dub. Dubbed. Dubbing of song will be there, na? Dubbed a song. Where he dubbed the song behind his metro. Where is his metro? In Darmstadtium. Right? Now the thing is, this mnemonic, it ends here, right? And after that you are having, this is Roger. Roger can never. So basically it is from Roger I am writing down, it is 89. From Roger I am writing here, in fact Roger can never have flavor of masala chai as he lives in Tennessee, Oganesson. So this is like entire line which is there. So this is Roger Federer I am talking about, legend of tennis. Roger can never have flavor of what? Masala chai. Masala chai available only in India, na? Masala chai. Why? As he lives where? In Tennessee. Oh God. We are saying whenever we got frustrated, oh God. So from there you take OG, right? So actually 60 series is only up to this, but from here right? This is like 111, this is 112, 113, 114, this is L, na? 115, 116, 117, and 118. So I have given you that entire row, okay? So it is 104, 105, 106, 107, 108, 109, 110, and this is 89. Getting it? So I've told you about the entire thing. Okay. So hopefully you people remember this. For F block, at present I won't be giving. Only while teaching you the F block, you will be able to relate. Now, let us talk about, so we have learned about period, we have talked about group. Now let us go for basically important points regarding long form of periodic table. Like these are very few things, but if at all you are able to remember, they'll be good. Okay. First one, 11 elements in gaseous form or else exist in gaseous form. So what are they? Basically, these are all the noble gases plus hydrogen plus oxygen plus nitrogen plus fluorine plus fluorine. So they are basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 elements. Right. Now the thing is liquid non-metal in the periodic table, that is basically bromine. Second one, liquid elements. Liquid elements means elements existing in liquid form at room temperature. Okay. So we are writing elements exist in liquid state at room temperature. So they are mercury and bromine. Mercury is a metal. Okay. Now next is elements which exist in liquid state just above room temperature. Just above room temperature. They are gallium, cesium, francium, and along with them it will be mercury and bromine, because their melting point is slightly more than kind of room temperature. Room temperature is 25 degrees Celsius, so their melting point is slightly kind of 27 degrees Celsius, around that. And they are when they are existing at room temperature gases or at room temperature liquid, definitely at above, slightly above, they'll definitely be in that particular liquid state. Okay. Now next one is metalloids. We also call them as semi-metals. So you're having these are that. Okay. So you can think of silly German asking sub-television and polished atta. Atta is pindi, actually you must be knowing polished atta. Atta is pindi, okay, in Telugu. Sub-television is the name of that. You might have seen a sub-TV, kind of that. Okay. Then, among lanthanoids, promethium, this is promethium, which is man-made element. Then, among actinoids, only these are naturally occurring elements. Okay, so you do remember all these like few points which are there, but they are going to be a little bit helpful for you. Okay. Now, next one we are going to go for IUPAC naming of elements having Z greater than 100. Z is what? Atomic number. So you are having digit and the name and the abbreviation. Sometimes the question can be asked from here also, right? So if for 0 it is nil, abbreviation is N. For 1 it is un. For 2 it is bi. For 3 it is tri. For 4 it is quad, right? For 5 it is pent. For 6 it is hex. For 7 it is sept. Don't write hept, okay? Which is like in IUPAC organic nomenclature, which we'll be doing. 8 is oct. 9 is ENN, right? So N here it is first letter actually. B, you are having T, you are having Q here, you are having P here. Here it is H, here it is S, here it is O, and here it is E. Now the name has to end with EM actually, right? That means suppose I have to write down 110. So that means nil EM. Are you getting it? If at all I have to write down 112, so this is un by EM. You won't be writing 2 of the I's. 120 if at all I have to write down un by nil EM. Getting it? I hope you understood how to name them, right? Got everybody? I hope this is clear to you, naming part. Okay. Now the thing is, they might have given you like this in one of the table which is given 101, 102, 103 and 104. Now the thing is 101 is Mendeleevium, Nobelium, and this is like Laurentium. And from here it is Rutherfordium. So you can remember from Rutherfordium you already know the tricks, because sometimes it could be asked identify the element 104 and they can give you not unnil quadium, they can give you Rutherfordium. So you should be able to identify. And here you should remember Mendeleev is a Nobel laureate, means the person who got Nobel prize. So you are able to remember Mendeleev, Nobel laureate, and basically Mendeleev, it should start with 101 is a good number, right? And 101 for Mendeleev, and Mendeleev has got tremendous contribution towards the periodic table which we are studying. So you should remember that for that regard 101 is Mendeleev, right? So I hope this is clear to you, right? I hope this session has been useful for you, right? So thank you and have a nice day.